My dear friends, we are running parallelly two subjects: transmission line protection using overcurrent and earth fault relays, and the engineering, procurement and commissioning of 66 by 11 kV substation. Today we will be talking about transmission line protection, and we have completed 9 sessions. To remind you, we have started with simple radial feeder. In that, we have seen different types of discrimination methods, and we have finalized the method of current time discrimination using normal inverse IDMT over current relays. And then we have formed the rules for phase relays and ground relays both. And we have calculated few examples also to let you know how to calculate the settings. Then we have entered into a new dimension of direction, that in certain networks, that means in many networks, in most of the networks, in all the states of the country and all the countries, I should say, uh, direction is a must, it is required. So we have seen where the direction is required. What are the networks? I mean, few networks we have seen. There can be many, but out of them we have seen few networks. Now we have to see how do we measure the angle between current and voltage. So in today's session we'll see how do we measure the voltage and current. So torque is proportional to 5V, 5I sine alpha, where alpha is the angle between them, right? For that, I think it's better I showed you the figure. 5I. 5I is in phase with I, and 5V is in phase with current flowing through voltage coil. But because voltage coil is highly inductive, IV is lagging the voltage by 90 degree. So phi I, phi V sine of angle between alpha. That is the torque. So if I write phi I, phi V sine of 90 minus 5, so that will give me cos phi. So torque is proportional to Vi cos phi. And if I say Vi cos phi, that means what? If phi is less than 90 degree, then I will get the positive torque. Less than 90 degree means in first quadrant. If I take x-axis as a reference, then in first quadrant if phi is less than 90 degree, and in fourth quadrant also in x-axis, negative x-axis, if it is less than 90 degree, torque is yet positive, because torque is positive in first, cos is positive in first and fourth quadrant. Second and third quadrant it will be negative. So that is how I am measuring the angle phi between the two quantities V and I. This you can read at your convenience by pausing the video. I'll show it in terms of the characteristics. Say V is the voltage. I am taking reference, right? And phi is the angle, that is power factor angle phi. Usually power factor is 0.8. So I have taken 36 degrees. So that is V, right? Now my torque is proportional to Vi cos phi, means at 0 degree. The torque is maximum because cos 0 is 1. But at that time, you see, what I require, say in electromagnetic relay, what was the requirement? That some small cup was rotating. It was rotating hardly by 1 or 2 millimeter. And the relay was operating. So relay was operating based on the cup. It is a simple principle as induction disk principle, which is used in overcurrent relays. There the distance is more. Here the distance is hardly 2 millimeters, because we do not want time delay. So what happens, that when the phi is 0, which is never the case. Phi is never 0. We do not work with resistive circuit. But as for example, if phi is 0, then current is already flowing. So what voltage will I require to make the relay operative? You see, at 0 voltage, relay will not operate because torque will be 0. Some voltage will be required. What some voltage? Some voltage is I have to rotate the cup. So some, howsoever cup may be of aluminum and very light, but some weight is there. So to move that weight, I will require some finite voltage. Not only that, but two contacts I cannot keep like that only. I have to I have to have a bias of slight bias of spring on moving contact so that by vibration the relay does not operate. So I have to overcome that slight bias of spring. So minimum voltage we mean, which is shown, the arrow is forgotten, but we mean is required, right? So that minimum voltage is required at 0 degree. Not only at 0 degree, but at all angles, some minimum voltage is required. At all angles. Say at 90 degree torque is 0, but at 89 degree torque is so low that I require very high voltage. Right? So at 88 degree I require very high voltage. So what I have to do? I have to rotate the voltage. If I am doing an experiment, I have to do an experiment using the phase shifter, and I have to phase shift the voltage from all 360 degree. So you see, you will see that at 88 or 89, I will get some reading. At 60, I will get some reading. Those points I have to find out, and that is the characteristic. So you can see that this is the characteristic of directional relay. This is a zero torque line. At 90 degree, it is zero torque. Beyond characteristic is all tripping region. Here the relay will trip. If the current is more than plug setting, then the relay will trip. On left hand side, there is a blocking region. Relay will block. Relay will not trip. Even if the current is more than plug setting. So this is how I am measuring the angle between voltage and current, my dear friends. So that one should remember. But you see, one has to understand that this characteristic, torque is maximum when angle is 0, is useless, because I want maximum torque when fault occurs. And when fault occurs, I have already told you that the angle is of the order of 75 to 80 degrees. So my maximum torque should be at 75 to 80 degrees. Therefore, my real formula should become the VI cos phi minus theta. Torque should be proportional to VI cos phi minus theta. Theta is a designed characteristic angle of a relay. That is unvariable. I mean, you can change by setting. That is a different thing. But that is relay manufacturer decide. Phi is variable because phi is dependent on the location of the fault. If relay is far from the generator, then resistance will be there, so angle will be less. And if the fault is near the generator, then angle will be practically 90 degree. So phi is variable based on fault location, right? So you see, if you keep theta equal to 90 degree and phi, as I told you, is about 75 degree, then T is proportional to VI cos phi minus the torque, you will get 96% of maximum torque. So you will get enough torque. So usually people go for phi, theta equal to 90 degree. And for going theta equal to 90 degree is very simple. Theta equal to 90 degree is very simple. What I do is I feed to the R phase. There are three relays. To R phase relay, I feed IR and VYB. Current, I feed IR. And voltage, I feed VYB, line voltage. Y phase, IY and VBR. B phase, IB and VRY. I feed this. So if you see this in vector diagram, the diagram is shown. Diagram must Yes, this is the vector diagram. IR and VYB. You see, VY minus VB, VYB. Angle between VYB and IR, considering zero power factor condition, considering unity power factor consideration, VYB and IR is 90 degree. Therefore, the name 90 degree. I am not doing anything in the relay. I will be playing with CTPT. I will be playing with CTPT. I will show you afterwards. But we were seeing this. Firstly, we were seeing this that we are feeding these quantities, right? So what we are feeding is these quantities we are feeding. So what is the problem when we make theta equal to 90 degree or theta equal to 75 degree? The characteristic will be something like this. Characteristic will be something like this. Sorry, not the characteristic. Actual characteristic is like this. That is operating zone, zero torque line, blocking zone, everything. So we need this kind of characteristic, right? And it will measure angle between theta and phi. Now, dead zone I am talking. Dead zone means the direction is correct, but yet the relay is not operating. So if you just see, this dead zone is not there in double line fault. Why it is not there? If there is an RY fault, say, then R and Y units are in picture. So I am feeding current IR and IY. Current is enough because there is a fault, no problem. Then to IR I am feeding VYB. Now even if RY fault occurs just after the relay, just after the breaker, then VRY is zero. Zero. Forget about 1 volt or 2 volt. It is just zero. Even then I am not feeding VRY. To R I am feeding VYB and to Y I am feeding VBR. VRY I am not feeding at all. So for double line fault there is no dead zone. For L2G, you see what I am feeding? Residual current IR plus IY plus IB, which is there for line to ground fault. And VR plus VY plus VB, residual voltage. Residual voltage I am feeding means VR plus VY plus VB is normally zero. But when earth fault occurs, VR plus VY plus VB. Now, if VR on R phase immediately after drilling point, if the fault occurs, then VR equal to zero. But then I am feeding VR plus VY plus VB. So VY plus VB is quite high. So there is no dead zone. So there is no dead zone in double line, double line to ground and line to ground. Dead zone is only in case of, only and only in case of triple line to ground when earthing switch is on and I am inadvertently making the breaker on. That will also, that these possibilities are also very less because there is an interlock. But if interlock fails, therefore the possibility is hardly 0.2%. In this case, the numerical relays give the facility of SOTF, switch on to fault. So actually dead zone is theoretical. There is nothing like dead zone. So this is to be understood. So what I was trying to tell, how we are measuring angle between the voltage and current. That is the main thing that we were talking about. So if we talk about this, then this is the case. That means for uh, no fault there is dead zone, so to say. In earlier case, when electromagnetic and static relays were used for RYB fault, the dead zone was there for RYB fault, triple line to ground fault. Then we were dependent on the upstream relay, backup relay we were dependent on, right? So that is the case with this. So this is all what I have talked about to you. So how the directional relay, this 90-degree correction, how do we arrive at? And physically, how do we connect? See, I am connecting 67R. 67 is the number of directional overcurrent relay. 67R in R phase, 67Y in Y phase, 67B in B phase, 67N in residual circuit of 3-line CTs. Then PT, come to PT. 67R, I am connecting between YB. You can check up. I am connecting between YB. 67B, I am connecting between RY. And 67Y, I am connecting between R and D. Right? So, dead zone problem is solved. Now, to earth fault relay, what do? I take out separate connections once again and have one more IVT, interposing VT, which is 110 by root 3 is to 110 by 3. So it measures exactly zero sequence voltage. And zero sequence voltage is present only in case of LG and LLG fault. So 67N will get a juice only for LG and LLG fault. So direction between 67N in current coil and voltage coil will be there. So earth fault is also connected. So this is how in directional relay physical connections are done. You have not to do anything in relay. 90-degree you have achieved. But in numerical relay they do give different angles. 0 to 360 whatever you want to adjust, you can adjust. So that is that. With that, my friends, I come to an end of uh, video tutorial number 10. There are 14 tutorials in transmission line protection using overcurrent and earth fault relay. We have, I think, now to talk about the relay setting in an interconnected system. We cannot take big system because we will need computer and all. I mean, that would be difficult. So we'll take a smaller system. But in that smaller system also, you will be able to rather, will be able to appreciate that it is quite complicated, right? And therefore, overcurrent and earth fault relays are not used in interconnected system. They are used, but they are used as backup, not as main protection, because they will give maloperations. So in interconnected system, that means in the systems 220 kV, 400 kV, 765 kV, overcurrent and earth fault relays are useless. Therefore, uh, they are used, but they are used as backup only, not as main relay. As main relay, distance protection you use, or yet better, line differential protection is used, about which I think we have talked also, right? So please read through these videos to increase the watch hours. Watch hours we have crossed 1,500 or so, but I want to reach first milestone of 4,000 watch hours, 4,000 view hours. So that only you can do. All people in the world, all my friends, all my electrical fraternity, uh, in industry as well as in academia, they can, they can, they can help me out. And it is not so that by helping out, I am not giving anything in turn. I am giving quite a lot much of knowledge in turn. So, and I am not asking for any money because it is on YouTube. So, not in terms of money, but in terms of watch hours. So please, and weekends, if you are not free daily, weekends, at least there must be quite a many engineers who are interested in power system protection. So 4,000 is a small figure. I think the number of viewers must be something like 8 millions or 10 millions. You see, that is what I think. That will not be immediately occur, but 4,000 should occur immediately. I have told my son that 4,000 will be by 15th July. Now let me see whether you are uh, you are making me correct to my son. My son told that is you are too much of you are thinking too much. It will not be that fast. It may be August or September or even more time. So if you want to make me correct, if you want to keep my statement correct and to prove my statement by 15th of July, 4,000 watch hours occurs, I'll be very happy. And I'll feel that you have paid me, not in terms of money, but in these terms. So my friends, thank you so much for hearing me patiently and good day.